In this lesson, you'll analyze and graph relations and find functional values. How do relations and functions apply to biology? The table shows the average lifetime and maximum lifetime for some animals. The data can also be represented as ordered pairs. The ordered pairs for the data are 1228, 1530, 820, 1220, 2050. The first number in each ordered pair is the average lifetime, and the second number is the maximum lifetime. The graph of the animal lifetime data lies in only one part of the Cartesian coordinate plane, the part with all positive numbers. The Cartesian coordinate plane is composed of the x-axis, or horizontal axis, the y-axis, or the vertical axis, which meet at the origin, which is 0, 0, and divide the plane normally into 4 quadrants. The points on the two axes do not lie in any quadrant. A relation is a set of ordered pairs, such as the one for the longevity of animals. The domain of relation is a set of all the first coordinates, or x-coordinates, from the ordered pairs, and the range is a set of all the second coordinates, the y-coordinates, from the ordered pairs. The graph of a relation is a set of points in the coordinate plane corresponding to the ordered pairs in the relation. An x-coordinate is sometimes called an abscissa, and the y-coordinate is sometimes called an ordinate. A function is a special type of relation in which each element of the domain is paired with exactly one element of the range. A mapping shows how each member of the domain is paired with each member of the range. So in this one we'd have -3 is paired with 1, 0 with 2, 2 with 4. The first two relations shown below are functions. We can pair them right across. If I know x is -1, I know you want a 5 for y. If you give me a 1, I know you want a 3. If you give me a 4, I know you want a 5. The third relation is not a function because -3 in the domain is paired with both 6 and 0. So if you give me a -3, I don't know what you want from me. Do you want a 0 or do you want a 6? A function like the first one below, where each element of the range is paired with exactly one element in the domain, is called a one-to-one function. State the domain and range of the relation shown in the graph, that is the relation of function. Domain, I'm going to be lazy and just put a D. It's just a list, so I'm just going to list my x's. I have 1, 3, 0, -4, and -3. If you look in the back of the book, they'll list them in order. Order is not important. For the range, my y's are 2, 3, -2, 0, and 1. And is this a function? Sure. Every x has its own y. So yes, it's a good rule. I know what I'm doing. Since this one's graphed, we could also use the vertical line test. If a vertical line only passes through the graph exactly once, it is a function. And we have two more examples of the vertical line test working and not working. If the vertical line intersects the graph in no more than one point, the graph represents a function. And then it won't work if some vertical line intersects a graph in 2 or more points. It is not a function. The table shows the average fuel efficiency in miles per gallon for light trucks for several years. Graph this information and determine whether it represents a function. They admitted that they skipped a few here with that little interrupter symbol, but otherwise they're going up very nicely by tenths on the mileage per gallon and then over by years. And then they just plotted their points, so 95, 20.5. And then to decide if it's a function, use the vertical line test. Okay, vertical line, vertical line. Usually I just lay my pencil down there and move the thing all the way across. But every vertical line I draw contains no more than one point. So yes, that is the graph of a function. And time is a good thing to graph a line over. We could connect the dots and make a line graph looking at trends. We spent lots of time in Algebra 1 graphing linear equations. We first learned to graph linear equation, which we'd make a table of values. Put 0 in for x, I get -1 out for y. Put 1 in for x, 1 times 3 is 3, minus 1 is 2. Put 2 in for x, 6, minus 1 is 5. Their chart looks nicer than mine and matches with the points that they plotted. But eventually we got to the point where we could graph this using slope-intercept form, which is y equals mx plus b. So my b, I can see the y-intercept is at -1, and the slope is going up 3 over 1. And we could graph the line that way. Domain is the list of all my x values. Okay, I have x values that I listed there, but I could have put in different ones. I did earlier. So domain, I could put in anything for x. And for the range, I'll eventually get out all real numbers for y as well. And this is a function because it's always going to pass the vertical line test. Every x will get its own y. The next graph we'll look at will be more curvy than linear. Now to graph this relation, we're going to have to break our normal rule when we make a chart and fill in the y values first and then the x. -2 squared is 4, plus 1 is 5. -1 squared is 1, plus 1 is 2. 0 squared is 0, plus 1 is 1. 1 squared is 1 again, plus 1 is 2 again. 2 squared is 4, plus 1 is 5 again. When we plot the points, it looks like a curve. It's called a parabola opening to the right. The domain, the smallest x can ever be on here, it looks like, is 1. So x is a number such that x is greater than or equal to 1. I can put in anything I want for y, so my range is all real numbers. This function fails the vertical line test, so it is not a function. Next, we need to be able to identify independent and dependent variables. When an equation represents a function, the variable, usually x, whose values make up the domain, is called the independent variable. The other variable, usually y, is called the dependent variable because its value depends on x. Suppose you have a job that pays by the hour. Since your pay depends on the number of hours you work, you might say your pay is a function of the number of hours you work. Equations that represent functions are often written in functional notation. The equation y equals 2x plus 1 can be written as f of x equals 2x plus 1. The symbol f of x replaces the y. The f is just a name for the function. It is not a variable that is multiplied by x. Suppose you want to find the value in the range that corresponds to the element 4 in the domain of the function. This is written f of 4. The value f of 4 is found by substituting 4 for each x in the equation. So in this example, f of 4 would equal 2 times 4 plus 1, or 9. Letters other than f can be used to represent a function. For example, you could write g of x equals 2x plus 1. If our function f of x is defined as x cubed minus 3, and they want us to find f of -2, every place there's an x, we're going to replace it with -2. So just using our PEMDAS then, -2 cubed is -8, minus 3 is -11. This has got decimals. I'm going to want a calculator. If we need to find h of 1.6, every place there's an x, I'm going to replace it with 1.6. And then I've got -3 times 1.6 squared is 2.56. -3 times 1.6 is 4.8 minus 2.7. And just finishing out our order of operations, multiply And I'm just copying it down and plug it into the calculator. And I get negative 6.732. It actually gets easier when they add variables. If I want to find f of 2t, I'm going to replace x with 2t. 2t cubed would be 2 cubed is 8, t cubed minus 3. They're not like terms. I can't combine them, and I'm done. A relation is a set of ordered pairs. The domain is a set of all the x-coordinates, and the range is a set of all the y-coordinates. A function is a relation where each member of the domain is paired with exactly one member of the range.